All right, bye-bye. Just for this week, we are going to have, so today, which is Tuesday, we're going to do section 4.1. Wednesday, we are going to do the M&M project. What's that? Wednesday. Thursday, we are going to do section 4.2. Friday, that's it out of chapter 4. Just these two sections, 4.1 and 4.2. We're going to review Friday and Monday. And then Tuesday, we're going to, I don't want to call it a quiz, assess over sections 4.1 and 4.2. Just those two sections. Sound good?
Yeah. Is that all of chapter 4?
That's all we're doing.
So that's technically our test.
Exactly, yeah. That'll be our test. It won't be as many points as the other tests would be, because it's only two sections, but it's still going to be the test. I have to call it a test because it's the end of the chapter assignment. So there is no project out of chapter 4. That M&M project is the project out of chapter 3. So, all right. So section 4.1, probability distributions. Section 4.1 and 4.2 are all different kinds of distributions. Section 4.1 is probability distributions, and section 4.2, I believe, is binomial distributions. All right. So for a probability distribution, again, when we start out, we got to make some definitions here. First one that we have is called a random variable. A random variable x represents a numerical value associated with each outcome of a probability experiment. A random variable x, random variable. All I'm saying here is that we are going to start calling the probability of an event P of x, right? And we're going to kind of make it open rather than say, probability of something. We're going to say probability of a variable happening. Okay, so P of x, because then we're going to start to make equations out of that stuff too. We're going to let it vary. So random variable x represents a numerical value associated with each outcome of a probability experiment. So like probability of rolling a 1, or probability of rolling a 2, or probability of getting a heads, or probability of pulling a 4, those types of things. A random variable is discrete. Now we have to understand the difference between the words discrete and continuous. And we talked about this in calculus as well, that idea of continuity. Continuous just means that there would be no gaps or breaks in the data. There would be no gaps or breaks in the data. Discrete meaning, okay, there would be gaps and breaks. What do I mean by that? Well, if I say I wanted to count the number of people in this room, is that a continuous or discrete? That's discrete, because that is a finite amount of things, right? There are 4. If I wanted to go and gather how many people are in each room of this building, I could find those values, and they would be singular solitary numbers, right? I couldn't have like a 0.5 or a 0.2. I could only have integers. I could only have whole values of that thing. That means it is discrete. It is not continuous because I can't have any number between those values. Like I can't have, any number between 3 and 4. I can't have any number between 15 and 16, right? It can't be like a 15.5, a 15.25. There are jumps in there. The next one up after 15 would be 16. The next one up after 16 would be 17. It is not continuous in between 15 and 16. Okay, so a random variable is continuous if it has an uncountable number of possible outcomes represented by an interval on a number line. Discrete is if it has a finite or countable number of possible outcomes that can be listed. So let's define some things to be continuous or discrete, and it has to be one or the other. It has to be continuous or it has to be discrete. And I gave you the example of counting people in the rooms. That is discrete values. They are finite. I can count and spit out the answer and then say, okay, yes, it is a finite number, right? So let's take a look here. Number of donuts in a box. Discrete, right? Discrete. What if there were even halves of donuts in the box? That's still discrete, right? that is still discrete because I can actually count how many pieces of donuts are in the box as well, right? It's not like it'd be even if there were halves, there'd be 4 and then 4.5, right? What about 4.1? What about 4.11? What about 4.111? We can't have that many amounts of donuts in that box, right? So therefore, that would be discrete. Let me keep going. Pounds of jelly beans purchased at a bulk candy store. Continuous. This is actually continuous because can I get? I always have to think about the word continuous because there's that UOU in there. It's really weird.
It could be any number.
Because it could be any number in between, right? Could I get 15.1 pounds? Yeah, 15.11 pounds. Yeah, 15.111 pounds. Yeah, I could have any number between 15 and 16 or any values in between there. That's why it has continuity. Oh, don't give me a table. What the heck are you doing? What the heck? Did I just make a table somewhere on there? Okay, whatever. Length of time to run a marathon. Continuous, right? Continuous. Because even though we may break it down in terms of minutes and seconds and probably round our answer, like round the time to the number of seconds, what about dividing it into milliseconds? What about dividing it even further than that? Could I? Yeah, if you wanted to. And that's why it has continuity. Continuous. What's an O here? Continuous. Length of time to run a 100-meter dash. Continuous again. Right? Continuous again. Even if it's a shorter length, it's still continuous because I could have any amount of time in between each value. Number of points scored in a basketball game. Discrete. Can I have like 31.5 points?
Oh.
Yeah. Discrete. So we have discrete data versus continuous data. You're going to find that like measurements, like temperatures, like times, like weights, things like that are normally more continuous. But again, think of countable things. Number of points that I can score. Yeah, those are finite values. I can't score an interval in between, but I can only score certain values. So then we have what's called a discrete probability distribution. A discrete probability distribution. A discrete probability distribution lists each possible value that the random variable can assume, together with its probability. So a probability distribution is basically like saying, here are all the possible outcomes that you could have, and here are all the probabilities that you could have. Could I possibly do this with something that's continuous? Could I possibly list out all values with something that's continuous? No, that's not even possible to do. So there is no such thing as a continuous probability distribution. There is only such thing as a discrete probability distribution because I can only list out discrete things rather than continuous things. So a discrete probability distribution lists each possible value that the random variable could assume together with its probability. A probability distribution must satisfy those conditions. Okay, so probabilities, we know from chapter 3, could only be between 0 and 1. It could be 0. It could be 1, right? You can't have a probability of 1.5. You can't have a probability of something being negative. That doesn't make sense. That doesn't exist. And what does that E mean? Sum of, right? So the sum of the probabilities in all our distributions should equal 1, right? The sum of all probabilities should equal 1. The sum of all probabilities should equal 1 in the end. So what we're going to do, and this is kind of a lot of work, a lot of handwriting, because what we're going to be doing is saying, okay, what are all possible outcomes of these things occurring? And then list out all the probabilities that we could have. Okay? All right, so let's do it with a probability distribution for rolling 2 dice and finding the sum. Rolling 2 dice and finding the sum. Well, the best thing to do here would be to kind of make a table. Yeah? Let's make ourselves a table. So the possibilities of rolling the first die is 1, 2, 3, 4, 5, or 6. And then 1, 2, 3, 4, 5, or 6 for the second die. Okay. You roll 2 ones. What's the sum?
2.
2. And then we roll a 2 and a 1, a 3 and a 1, 4 and a 1, 5 and a 1, a 6 and a 1. We can fill in this table, right? This is pretty easy. 2 and a 2, 2 and a 1. That's a 3, 4, 5, 6, 7, 8. Okay, 1 and a 3. That's a 4, 5, 6, 7, 8, and 9. Okay, 4 and a 1. That's a 5, and a 6, and a 7, and an 8, and a 9, and a 10. 5 and a 1. That's a 6, 7, 8, 9, 10, 11. And then 6 and a 1. That's 7, and then we have 8, 9, 10, 11, and a 12. Those are all possible outcomes, right? I have just listed off all possible outcomes for rolling 2 die. Rolling 2 dice. Now, this is obviously discrete, right? Because I can count the number of the sum, a finite number. So this is a discrete probability distribution. So the discrete probability distribution looks like this. I have to show the probability of getting a 2. What's the probability of getting a 2? Rolling a sum of 2.
It's like 1 out of all numbers.
How many are there? 6 by 6 table.
36.
136. Okay. So what's the probability of rolling a 3? 2 out of 36. I'm going to leave it as 36 here in a second. Oh, I just wrote 3. Whoops. That's a 2 out of 36. Probability of 5, probability of 6, probability of 7. I'm going to list these off. Probability of 8. You know what? Let me jump up here. Probability of 9, probability of 10, probability of 11, probability of 12. This all total is a probability distribution, listing off all possible outcomes and their probabilities. Okay, what's the probability of rolling a 4? 3/36. Rolling a 5? 4. I know I could reduce that to 1/9. 5 out of 36. 7, 2, 3, 4, 6 out of 36. And then it starts to wrap around again, right? Then we see, okay, 1, 2, 3, 4, 5 8s. 4 9s. 3 10s. 2 11s. 1 12. What's the most commonly rolled number? 7. That's why you guys ever play Settlers of Catan? You guys ever play Settlers? No.
I've heard of it.
When you roll a 7, something special happens. So there's our probability distribution, right? There's our probability distribution. What I wanted to show, why I didn't reduce these fractions is because what would happen if I added up all of those probabilities? I would get 36. Look at all the numerators. 1 plus 2 is 3, 6, 10, 15, 21, 26, 30, 33, 35, 36, 36. Yeah. The probability distribution should add up to 1 in the end. So that whole thing is called the probability distribution. Now, was this experimental or theoretical probability? Theoretical, right? Did I actually roll these dice? No, because that would be an experiment, right? This is more theoretical. Does that work the same way for experimental? Yeah, works the same way for experimental. An industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Each individual was given a whole number score from 1 to 5. Now, what does this tell you? Just that phrase right there, that this is discrete. right?
Yeah.
Each individual was given a whole number score from 1 to 5. So that means this data is discrete. There's not a possibility of 1.5 or 2.5 or anything in between 1 and 2, rather. Where 1 is extremely passive and 5 is extremely aggressive. A score of 3 indicated that neither trait. The results are shown in the table. Construct a probability distribution for the random variable x. All right, so basically what I want to do here is find the probability of these things occurring. Now, what is the probability for a frequency table? Well, you've got to find the relative frequency, basically, right? The relative frequency. So how many total people did I study? 150. Okay, so 24 out of 150. We're going to get my calculator up. (24) out of 150 gives me 0.16. 33 out of 150 gives me 0.22. 42 out of 150 gives me 0.28. 30 out of 150. That's not right. 0.2, right? And then 21 out of 150 gives me 0.14. That is my probability distribution, right? I guess showing the whole table. Maybe I should have said P of 1 is 0.16, P of 2 is 0.22, P of 3 is 0.28, and so on, right? I should have really done that. But this is just fine in and of itself. That's my probability distribution. Okay. What we're going to go further, and I think this comes tomorrow, if not tomorrow, then the next chapter, is we think about, okay, well, what if I plotted these? Since they're an x value, what if I plotted these distribution? Or what if I plotted this distribution? You know what it would come out to be in this case? Bell-shaped, right? Bell-shaped. What does it kind of come out to be here? Bit of a bell shape, right? And that's what we're going to be getting into a little bit, as we progress through. Okay, if these things are bell-shaped, what can we say about them? And then what can we predict about them? If we chose a person at random, or if we chose a person what could we expect to see out of a population? How many would we expect to see? And that kind of leads me right into here. Mean of a discrete random variable. Mean of a discrete random variable. The mean of a discrete random variable is given by mu is equal to the sum of x times p of x. And that is a sum of all of these things, not like sum of x's times p of x. It is the sum of x times p of x. It is the sum of x times p of x. Now, this is called the this is called the mean of a discrete random variable, right? What I like to call this is expected value. Expected value. This is the term I like to use. Expected value. Like, for example, if I take a look at that last study and I say, if I chose a person at random, what is the value that I would expect to see? What is the value that I would expect to see if I chose a person at random and gave them that same study? Well, I would think it would probably be coming out to somewhere around 3, right? How do I find that out? Well, I basically just find the mean, right? I find the sum of x times p of x. Now, that formula should look a little familiar. That formula, isn't that the formula for the mean of a frequency table? Sum of x times f, right? Sum of the number times the frequency. That's the exact same thing, right? That's the exact same thing. So it's finding the sum of that x times p of x. Okay, let's do that. Find the mean of the probability distribution. Now this has 0 context to it. This is just saying, okay, these are my values, 3, 5, 8, and 12. Discrete random variable. I only have the options of getting a 3, a 5, an 8, or a 12. And then we can say, here are my different probabilities. This doesn't necessarily look bell-shaped, right? But I want to find my mean of my probability distribution, which means I'm basically finding my expected value. Okay, so I'm going to add on another column here, and I'm going to find x p of x. Okay. So what I'm going to do is take 3 times 0.2, and 5 times 0.25, and 8 times 0.4, and 12 times 0.15. Okay.
Thank you.
I've got 0.6, 1.25, 3.2, and 1.8. Right? And then I find the sum. Okay, so I'm going to take 0.6 plus 1.25 plus 3.2 plus 1.8. 6.85. So that is my mu, right? So that means that if I chose a person at random and gave them this exact same treatment, whatever this thing is, ran this exact same thing, whatever this is, that has no context, the expectation is that they would get a 6.85 within the data.
Discrete. If it was discrete, would we say 7?
That's a good point. That's a good point. We're just going to say the expected value is 6.85. Leave it as a decimal. Leave it as a decimal. But that is a good point that it would bring up about that. All right, so just like we could find the mean, we can also find the standard deviation and variance. Yeah. So how do you find these? Now, again, this is all going to be on your formula sheets, so there's no need to memorize these things. So what does this actually mean, though? Well, what is this thing? That's your deviation, right? Your deviation, x minus mu. How far does that thing deviate, away from the mean? Squared. So your deviation squared times your probability. So it's your deviation. It's the probability of your deviation, basically. And then you find standard deviation by square rooting that whole thing, which is a common theme, right? Standard deviation is always the square root of the variance. Standard deviation is always the square root of the variance. Okay? So how are we going to find this? Well, we're going to take x minus mu squared times p of x. X minus mu squared times p of x. So let's run that exact same thing. Same treatment here. Same thing. All these numbers are the exact same thing. Now my mu, what do we say, 6.85?
Yep.
So now all I'm going to do is make another column and say, okay, I want to find x minus mu squared p of x. Right? And then I'm going to find the sum of all of that. Okay. So I'm going to take x, you know what, I'm going to put this in parentheses. X minus mu 6.85 times p of x times 0.2. Oops, squared times 0.2. I'll put that in parentheses for good measure, just so to partition it off a little bit. You follow me here? X minus mu squared times p of x. 2.96, we'll round it to. 2.96. Do the same thing, but instead of an x value of 3, I have x value of 5. Still subtracting away the 6.85, but now my probability is 0.25. 0.85, what I rounded to, 0.86. 0.86. Same thing here, but now my x value is 8, and my probability is no longer 0.25, but it is 0.4. 0.529, so 0.53. And lastly, come on I want to do my 12 with a probability of 0.15. 3.98. Okay, so the sum of that is going to be my variance. 2.96, 0.86, 0.53, 3.98. 8.33. Just make sure I plug everything correctly. Yep. 8.33. So sigma squared, which is our variance, is 8.33. So let's figure out our standard deviation. Square root of 8.33 is 2.89. You know, we can tell a lot more by standard deviation than we can by variance, right? So we can say that the mu is 6.85 with a standard deviation of 2.89. And then we can tell a little bit more about that. We can say, well, if it's 1 or 2 standard deviations away from the mean, we know it fits within certain percentiles and certain percentages, right? Now, there is an assumption that this might be more bell-shaped. Well, then we have to go back to that Chebyshev's rule where it's like, okay, well, if it's not bell-shaped, because this doesn't really look bell-shaped, if it's not bell-shaped, you got to do that 1 minus 1 over k squared. But we can tell more about the probability distribution based off of sigma than we can off the variance. We can tell more of the standard deviation based after or in contrast to the variance. Okay. Okay, last thing we're going to talk about. I like this problem. Expected. Goes right along with expected value. At a raffle, 1,500 tickets are sold. $2 for each of the 4 prizes. And we got 4 prizes. I always get roped into doing these for students. Oh, I got this raffle ticket. You could win $500. But like, what's your expected value on that? You know, like, really low. Probably like, what's my return on investment? Probably what?
0.
Probably negative, right? I'm probably going to be losing my money, right?
Yeah.
But maybe not.
But maybe not. But there is a probability that I may not be, right? So what is my true return on investment? Like, I always think of this like as a card player. Like, what's the probability if I throw the money in? What's the probability of me hitting my card? And if it's worth that bet, what's my return? Like, what's already in the pot? What can I win based off of that? This is a more simple example where it's just a raffle. It's got 1,500 tickets, and there's $2 each for tickets, but it's got 4 prizes, right? It's got 4 prizes. So let's think about this in terms of like a probability distribution, a true probability distribution. So I've got a $500 winner. I've got a $250 winner. I've got a $150 winner, and then a $75 winner, right? Let me get out my notes. I don't want to screw up the table. Hold on. Okay. So for my $500, or I could win nothing, right? I guess that's my other option. If I won $500, what's my return? What's my net? $498, right? Okay. Obviously, if I win the 250, $248. If I win the 150, that's $148. If I win the 75, that's $73. If I win nothing, what's my net? -2. Okay, that's my discrete random variable. That's my x. Because that's all of my possible outcomes. I could net $498 or $248 or $148 or $73, or I could net -$2. So to find my probability distribution, I would take, to find my probability, well, how many total tickets? 1,500 tickets, right? 1,500. How many of them are a $500 winner? 1. So there is a 1 in 1,500 ticket chance. I pull that. How many is the $250 winner? 1 out of 1,500. What's the probability of me picking the $150 winner? 1 out of 1,500. 1 out of 1,500. What's the probability of losing? 1,496
Those are
out of 1,500. Now, to find my expected value, which is my mean, right? My mean of my probability distribution is the expected value or return on investment, the expectation of money getting back, right? If it's a true raffle, should I be expecting any money back? No, I should be expecting to lose money, right? It's probably benefiting something, right? Now, if that's the case, I want to try to find my mean. Well, my mean is again x p of x, and I forgot to write sigma of x p of x, right? So let's calculate x p of x. So x is 498 times, whoa,
that's a big number.
times 1 out of 1,500. 0.332. Right? X p of x, 0.332. All right. Same thing, but now 248. 0.165. Same thing, but now 148. 0.099. Same thing, but now 73. 0.049. Same thing, but now, come on, come back. Come back to me. They're watching Encanto over there. Let's go. I've got -2 times, 1496 divided by 1,500. -1.99.
I never watched Encanto.
It's a good movie. So the expected value,
The one where all the music came from. Like the one-
0.332 plus 0.165, 0.165, plus 0.099 plus 0.049 plus -1.99. Right, so for every ticket I purchase,
You're losing the buck.
I'm losing $1.35. For every ticket I purchase that costs $2, I'm losing $1.35. Okay, and that factors in all the amounts that I could win too. Does that make sense? So if you ran this calculation and it came out positive, you buy all the raffle tickets because they somehow did they're giving away more money than they're taking in, right? Which is not a good business model. So we're saying that the return on investment, my $2 investment is going to return a negative $1.35. Bad investment, right? Obviously, a raffle ticket is a bad investment. You're helping somebody out. Yeah. All right, let me stop the video there.